Okay, cool. Hello, everybody. It is our May community call on the very last day of May. So we made it in before June started. I'm really excited. Run of show today. We're going to bring on some of our key partners in the developer tooling ecosystem, which makes me super excited. And then hop on over to one of our researchers to talk about um, our approver and then have some really important engineering updates for you guys. Uh, but yeah, so we'll go ahead and get started. I know Hilmar needs to leave super soon, so I'm just going to go ahead and kick everyone off and then bring him on. And we'll try to talk at the speed of light, but I guess these are the other faces you guys can expect to see later in the stream. So goodbye, Alexandre. Goodbye, Kiara. Goodbye, Milan. Hello, Hilmar. Okay, cool. Let's go get started. First off the bat, please introduce yourself.
Hey Emily, good to see you.
Hello.
Long time. You
Yeah,
changed your hair?
I
On the,
did. Oh,
you
people,
changed your hair?
maybe people don't know the history of us. Please check out the Truffle YouTube. We did a workshop together on gelato automation,
Yeah.
but gelato does too many things, so you're coming back up to talk about something new. But yes, my
Yeah,
hair is
good to
different.
good to good
Thank
to
you
be
for
here.
noticing.
Of course, always.
Yeah.
Yeah. Hi everyone. My name is Hilma. I'm one of the co-founders of Gelato. Gelato is Web3's decentralized backend. And yeah, we started Gelato because we realized that building smart contracts and building Web3 applications means not only that you have to write smart contracts, but there are a bunch of like server-side components that you need to take care of when doing so in order to really provide a really good user experience to users, in order to provide actually feature-rich and build feature-rich applications. And yeah, this is why we built Gelato. And Gelato focuses really on three core services that we offer to all of you guys that might be developing on Linea, for example. And first of all, this is a gasless transaction. So Gelato has a decentralized relay network where developers can provide the users with a super slick UX without having or without asking them to use or have to purchase like the network token to pay for gas. They can just like click a button and transactions are being sent on their behalf across like a 10, 12 or 14 different chains. And I think, yeah, I actually just checked. I think we like on the test net of Linea, a Gelato relay is used quite heavily. I think, right? Pretty
I
sure.
I don't have those numbers, but
Yeah,
I trust
I
you.
I actually have the numbers here. I think we have over 600,000 transactions that have already been executed. I think
What?
we burned through like I don't know, uh, 1,000 ETH or something. I don't know what's
Oh
like the
my god.
test net ETH, right?
Yeah.
Yeah, that's pretty heavily used. But not only for this, I think it's questing or something that goes on there. I'm actually not too sure about it. But yeah, it can be used for gases, NFTs, minting, game interactions, all sort of cool things. But this is not all what Gelato does. Gelato does also a bunch of other cool things because we actually started with smart contract automation. So we help developers automate a bunch of cool use cases because, yeah, smart contracts are not smart. They're actually quite dumb. They don't react and don't transact themselves. You need someone to transact on their behalf. And this is usually an outside party like Gelato. And you want this to be a decentralized network that does it. And this is the job that Gelato does, for example, executing limit orders on PancakeSwap or Uniswap or one of these dexes is a very common example of that. And then also with our latest Web3 functions that we released, we now enable projects to connect their smart contracts to not only like data from the same chain, but basically to off-chain data. So you can call any sort of arbitrary APIs and connect these APIs. So basically Web2 world to your smart contracts in order to plug in, let's say, social media data, tweets, or you can plug in the result of a football or soccer match for a betting website or whatever you want to build, you can build it. And yeah, our aim is to provide you with all the backend tools you need in order for you to just have to build your smart contracts, deploy it, and that's basically it.
Oh, that was a lot. See, this is what I
Yes,
meant by Gelato does too much, so we have to bring you on like all the time.
definitely.
But very glad you're on, Linea. I guess today I wanted to speak to you directly about the relayer because that is what you
Mhm.
currently use on Linea. So can you give us an overview, kind of like what it is and the plumbing behind it? Um, yeah.
For sure. I can maybe just quickly, shall I just share my screen? Is that possible? I think
It's
so, right?
possible. We'll see
Yeah.
if it's blurry, if it's having issues.
Let me. Do you see that?
Yes, yes. Okay, cool.
Cool. All right. So by the way, here are the smart contracts that I just mentioned. The Gelato one, 330,000 transactions. Um, and this one is like 319,000 transactions. So a bunch of and they're just keep just getting hit. I don't know what's I think it's just some questing or something, right? All right, cool. So what is like as transaction, right? Let's do that. Let's say you're a user, you want to sign in. This is, by the way, like a Web3 auth flow, so you don't have to create like a seed phrase and write it down or something. So this is usually how you can combine Gelato with, for example, with Web3 auth here. In this case, we are on Girly. And what we can do here is we can say we want to mint an NFT. And of course, we don't have ETH right now in our wallet to pay for that, but we still want to do it. And so what we can do is we can click mint. And what it does, it actually sends a request to the Gelato network. And Gelato is a decentralized network that consists of node operators. And it basically gets this request. And I actually signed a message in the background. It wasn't shown because it's Web3 auth, but I signed a message, which was my intent to mint this NFT. And bam, you can see suddenly it got minted, even though I didn't have had any ETH or I didn't want to send any transactions myself. And you can see 22 seconds ago, this was executed. Some NFT was sent to me, and you can actually check it out right away on OpenSea. And bam, it's there. It's this cute gelato thing is jumping around. So this is basically the power of gaseous transactions, and you can witness this on a bunch of NFT platforms or games, or there's this cool sporting website, I forgot what it's called, where you can mint shares of your favorite tennis players. And if these tennis players win like a championship, let me just stop my screen share. If the tennis player win a championship, then you earn like parts of the prize or something, and you can actually, without having to send a single transactions, only by paying with USDC, by just signing some messages that get relayed by Gelato, interact and buy this NFT, right? Which is, I think, exactly what the future should be. You shouldn't be asked to send transactions all the time, right? And this is basically what Gelato Relay enables, and super simple, just an easy API. It's compatible with all sorts of ways of how you can get transactions mined on Ethereum or other EVM chains. And so yeah, it's pretty easy to use.
Okay, very cool. Okay, I have you in person, so I do want to ask you a really fast question. I've been toying around the idea of building a Web3 RPG where you go around and like collect cat toys. Is Gelato Relay like fast enough that I could just like, instead of like minting it, right? The idea is like I hit space bar and then I collect it into my collection, and then what's that time delay between
Yeah.
collecting it and then
So you mean what's the time delay between actually getting transaction on chain and then knowing about it, right? And the user not feeling it, right? So there, Gelato's like the latency overhead that is sort of the most important one is actually the ones from the RPCs, right? So Gelato system is very fast. So like it depends on like how quickly these RPCs get these messages broadcasted to like a sequencer or whoever should receive it, right? And then reflected back on the UI to get the response that something was included, right? That's basically the overhead. And so that kind of depends on the chain, right? Of course, with Linea, we work together with you guys, and then on other chains, we work together with other RPC providers, run our own nodes and stuff like that. So we want to get that down to as fast as possible. But yeah, so RPCs are usually the biggest bottleneck, and then we are talking like sub-seconds. And then, of course, block time is the other latency that you have to take into account here. But what you can do, what other projects do, if it's a transaction that sort of cannot revert based on like state changing after like in a consecutive block, for example, right? Let's say you just want to mint an NFT and everyone can mint this NFT, then you can, what I call, optimistically already change the state on your UI that it shows that it was already included without actually waiting for the response from the request, right? So that's, for example, how Lens does it, right? Lens just has like a shit ton of people posting, and what they do is they just like collect all these posts, and then like after 10 minutes or so they can just like in one batch send them all to the chain, but they already show it to you as if it was on chain already, because it cannot really not get included because there's no front running or something, right? And this is, I think, how applications should be built.
Okay, thank you. That was very helpful. We are already over time, so I guess I want to fast forward to our end questions. First off, for our Linea developers, is there anything that they should keep in mind? Like, is it different at all from developing with Gelato on Ethereum?
I think not. I think it's pretty much the same, if I'm not
Okay, good.
mistaken.
Yeah, that was a baited question, so we can move on.
Yeah.
Yeah. Anything you want to announce, I guess, for Gelato?
Um, oh yeah, so we recently released our newest release of the Web3 function private beta, which is this basically decentralized cloud function service that we offer, where you can connect your smart contracts to the off-chain world and call any sort of APIs. Super slick. It's now much more performant. You can you can query the state of 10 different chains in one sort of function, and then sort of see which ones you want to send transactions to and stuff. It's a bit detailed, but yeah, check it out. Web3 functions, private beta, Gelato, Google it and find it out. And I think you will like it. So yeah, that's it.
Okay, cool. I guess last piece is I think you guys will be joining us for a workshop on like actually how to build on Gelato. So keep an eye out on that.
Oh yeah.
But I will let you go. Um,
Yeah, thanks. It was
goodbye.
a pleasure to be here, Emily.
Yes,
Ciao.
yes, of course. Okay, cool. So next we have Kiara coming on from thirdweb. So Kiara, please introduce yourself.
Hello, hi everyone. My name's Kira. I'm a developer experience engineer at thirdweb. I actually make example apps and make educational content, the docs, and just do everything to help improve the developer experience at thirdweb, because that is just one of the main things that we are focused on, is just making that developer experience as amazing as possible, so that you guys can onboard as many users as you possibly can. So should I do a little description of thirdweb and what
Yeah,
we
go
do?
for it. Yes, tell us about thirdweb.
Okay. Okay. So hang on, let me just share my screen really quick. Uh, okay, cool. So thirdweb is basically a way for developers to build Web3 apps and games. So we offer everything that you could need for your development needs for building these apps, from the smart contracts all the way through to your front end. On our website, which is just thirdweb.com, we have a nice little graphic that just explains everything that we do, because we do have a lot of different tools and products. So we have solutions for writing your smart contracts, like I was saying. So we have a Solidity SDK. We have pre-built contracts on our explore page, which I'll show in a second actually. And then we have different SDKs which can recognize the standards, or what we call extensions, on your smart contracts. And that means that you can then view a dashboard to manage your smart contracts, interact with the functions on your smart contracts, and then also build that into a front end, or like a back end. Like, so we have a Python SDK, we have a Go SDK, a JavaScript one, JavaScript or TypeScript, React, am I missing anything? Oh, of course, Unity. And then we also have a CLI, which allows you to deploy contracts easily, to publish them so that other people can deploy your contracts, and so many other tools. We also have some infrastructure tools. So recently we released our wallet SDK, which has lots of different solutions for building wallets into your apps. So that means that you can easily integrate it into a script or a backend, but then also into your front end with our React SDK. And together with our Connect Wallet button, you can easily add any wallet that you choose, through Wallet Connect, but then also we've got pre-built components that you can use as well. And then we also have, as part of that wallet SDK, our local wallet, which is basically like a walletless and transactionless experience. And then also an account abstraction implementation that makes it easy to build smart wallets into your apps. I know that was a little bit of a like messy overview, but there's so many different tools, it's very hard to give a synopsis. I can give a demo of some of them, but yeah, I think that's a good sort of like baseline.
Yeah, thirdweb does a lot. But yeah, like you mentioned, this is actually really great for like Web3 use cases. I think especially since people aren't like for people who are new to Web3, right? I think that's where kind of thirdweb sits as a layer for making that kind of switch over very painless. So, I guess kind of things I'm thinking about, right? Like, especially for Linea as a new ecosystem. We're still on testnet, right? Third web obviously enables developers to build really cool things. Is there anything like if someone was building like your dream dApp using third web's capabilities on Linea? Maybe this is putting you on the spot. Like, do you have an idea or something cool that you've seen? Um,
I think the coolest examples we've seen tend to be the gaming examples, because the current solutions for gaming are, in my opinion, don't match our Unity SDK. Obviously, I'm biased, but our Unity SDK is just like incredible. It makes it so easy to build Web3 games, which do not feel like they are Web3. You don't know, and using the Unity SDK alongside the Wallet SDK means that you can not have to interrupt game flows, so you don't have to connect to Wallet. So that all happens under the like behind the scenes. You can create a wallet, and then the in-game assets can be accumulated in this wallet without you having to sign transactions, without any gameplay having to be paused, and then you can export those assets out at a later date to your EOA, like a MetaMask, or you could build a smart wallet into your app so that you don't have to worry about those kind of things. And I think the main thing that we want to see is just people using our tools to build really cool games. We spoke to so many. I actually went to the Avalanche Summit a couple of weeks ago, and a lot of the games there were saying, there are no solutions for onboarding these Web 2 natives, and I think we provide that solution because our whole thing is about making it easy for Web 3 developers to onboard their users. And I think that's ultimately what I like to see.
Okay, awesome. So I guess same question as before. For developers building on Linea, if they built with Third Web before, is there anything they need to keep in mind? Are all of Third Web's functionalities available for Linea developers yet?
Yes, absolutely. So we are
Okay.
any EVM compatible. All of the tools will work for any
Wow.
EVM actually. So so the no limitations there. I also just wanted to touch on, I think in the past we've definitely been more of like a get people started quickly kind of tool, but as we've grown, we've grown more into, we think of ourselves as
Oh,
I'm
sorry.
not showing the words. Fine. No, don't worry about it.
Oh, okay.
We think of ourselves more as like the wrapper on top. We give you one single platform for all of your needs, because onboarding onto Web3 development has this incredibly steep learning curve, right? And there are so many different providers and platforms and different things you need to learn. Like, you need to learn Solidity, you need to know what an RPC is, you need to understand, what chain ID to use, and all of these kind of things. And connecting that to your app, and like you then have to learn like another SDK to build it into your app, and these kind of things. And all of these names, all of these different platforms, all of these different things to learn, it's just so messy. And we don't have that in Web 2. In Web 2, we have these companies that kind of wrap everything together. They do all of the heavy lifting for you. And that's what we aim to do. It's not necessarily get you started quickly, but then ultimately you need to learn these things. It's more like we provide the defaults. We do all of the heavy lifting, so you never have to. You don't limit yourself in terms of what you can build, or the amount of technical flexibility you have, because all of these defaults can be overridden. It's completely customizable, and you actually end up spending more of your time on the technical specific details that are specific to your project, rather than having to spend all your time on the heavy lifting, rinse, repeat, writing Merkle trees and Merkle roots and all of that kind of stuff. Like, you don't have to spend your time on that. You can spend your time on the more technical specifics.
Okay, very cool. So, I guess, do you have any updates for Third Web that you want to give? Alpha? That's the real thing I'm looking for.
Alpha. I think that's really difficult. I think our Unity SDK is already like top notch. The guy who builds everything for our Unity SDK, he's like one of the most amazing engineers I've ever met. And we are doing a big revamp of that at the moment, so keep your eyes peeled for that. And then also we are looking to release NEA EVM for our publish feature, which is basically like where you can have any contract and then you can publish this contract so that your users can come and deploy instances of that contract. And previously, if you were deploying with like proxies or factories, you would have to have an implementation on every single chain. And now with deterministic deployments, you don't have to do that. I think that is a really cool feature that we are releasing soon. I'm trying to think if there's any other alpha that I'm able to share.
No, it's fine. Just text me afterwards and I'll blast it on our Twitter, right? But anyway, thank you so much for joining. I'm really excited for thirdweb. I did want to mention, well, actually, I'll mention this after Hal comes on, but I guess look forward to the next section. Anyways, thank you so much, Kiara. I'm going to kick you
So
off.
much.
Goodbye. And then my beautiful coworker, please introduce yourself.
Hey, Emily. Hi, everyone. I'm Melin. I am a business developer at HAL, and we've been recently acquired by Consensus. So yeah, now I have the pleasure of working with you.
Woohoo! Okay, that's the most important thing. You can leave now. But yeah, okay. So please tell us a little bit about HAL.
Yeah, so the project really started off of the idea that the blockchain data is usually a bit hard to access because it's not very obvious what happens, and we saw people spending like lots of time on Etherscan and stuff like this to really understand what happened. And so the idea that we had is we built an engine that would listen to the chain, and users would be able to let that engine know what they wanted to be notified about. And so that engine is very general purpose. And so the first application we built was notifications. And so we've been working with a lot of friends in DeFi to provide notifications to their services. And after that, we realized that, yes, this notification is essentially one application of that engine that is quite powerful. And so we decided to create a new product that is called Stream. And this one is much more developer focused. And the idea is that it enables you to essentially turn any Web3 smart contract into an API and then connect that data to regular pipelines like a webhook or a database or something where the rest of your workflow is. So it's a bit of a bridge between Web3 and Web2, and it enables you to take that data on chain and have it directly accessible to the rest of your system.
Okay, very cool. Okay, so now we know what HAL is. I'm curious if you've seen any really cool use cases or kind of HAL in the wild. Am I even pronouncing that correctly? Is it HAL? HAL?
Yeah. HAL. Yeah, HAL.
Okay. HAL? Okay.
But
as an American, I should say HAL, right? Like from Texas.
you do you.
Yeah.
No, but the main thing and the biggest use case we've seen is when we early on we partnered with Aave, and Aave was we were one of the grant recipients of Aave, and we have been integrated with them. And so now when people go on Aave and they want to be notified about their health factor being a bit unhealthy, they by default on the interface, when they set this up, they are using HAL to avoid getting wrecked, essentially. So yeah, this is one of the first use case that we had, and that was for the first product. The second product is actually used by the Infura faucet, for example, to get Gorley and Sepolia ETH. HAL Stream is used in that workflow to enable users to get that Gorley ETH to do all of the Linea quests that they want to do.
Yes. Actually, now we have Linea ETH dripping directly to your Linea network.
Amazing.
Faucet on Linea. Cool. I'm gonna. Oh, where did it go?
I see it in the chat.
You see it in the chat? Yeah. Oh, nope, I spelled Infura incorrectly. Let me try again. But yes, okay, cool. So for people building on Linea with HAL, is there any kind of gotchas they need to look out for?
No, like the good thing is it doesn't change anything. Like Linea being essentially from a developer perspective, being exactly the same as this Ethereum, you can use how stream, how notify, exactly how you would use them before. So there is no like learning curve or anything specific to using Linea. It's really plug and play. Even when we started supporting Linea, it did not cost us more than half a day. Like it was very, very straightforward.
Okay. Very cool. So, I know we just merged this morning a tutorial from you. So let me link to it. If you guys actually want to start playing around with Hall, community tutorials. Here we go. I found the link. Now I will post it in the chat. There you go. Do this. Oh wait, nope. I posted the blog.
It is in the
It's in the blog. It's in the blog. I don't want to keep making
it's the right link.
Okay, here we go. Go here. He wrote this. It's very good, very thorough. I'll give you like a little bit of an introduction. But again, okay, cool. We are, I think, at time. Is there anything else you wanted to announce, talk about, what you're excited for, compliment Linea?
Yeah. I don't have much alpha to give you. That is one thing, and I'm sorry for this. But no, like now that we have been acquired by Consensus, the good thing is that that whole engine and technology that we've been building is gonna start to get into every product that Consensus touches. So it's gonna be interesting to see how we can further enhance the products that we already have. And yeah, of course, Linea is definitely one of them.
Okay, very cool. Thank you so much. I will kick you off.
Thank you, Emily.
And I'm going to bring someone actually on from the Linea team.
Hello, everyone.
Hello. We've gotten past the developer tool. So if you're a developer and you're building, like, this is what you should be working with. Now we're in the section where you're like, what even am I working with? And that's what Alexandre is here to talk about. So if you want to start, please introduce yourself.
So hello, everyone. I'm Alexandre. I've been working at Consensus for 5 years and been working specifically on cryptography research for 3 years now. And I'm at Linea. I'm working on the design, the implementation, and the publication of the proof system that we use for the zkVM. And I'm going to make a presentation unless you have a question before that, Emily.
No, just go ahead and get started.
Okay, let's go.
Go. I do want to note for our watchers out here, you need to focus like 100%. This is a lot of information.
I will try to make it accessible.
Okay.
Okay, can you see my screen?
Mm-hmm.
Okay, perfect. So yeah, I'm going to explain to you, to tell you a bit about ZK text that we are deploying for the Linea prover. So first of all, why do we need a prover and why would you do ZK at all? So first, let's look at how the Ethereum network works as a whole. So concretely, the Ethereum network can be summarized as a mesh of multiple Ethereum nodes communicating to each other in a peer-to-peer fashion. Concretely, in this network, all the nodes are susceptible to emit transactions and propagate them throughout all the peers. And so that's great if you want to propagate or gossip transactions from the users. But it does not solve in which order are the transactions. So for that, we have a consensus engine. And on top of that, we do have what we call a virtual machine. And the virtual machine is some sort of computer that is run by the entire set of nodes. So you could think of it as a world computer. Everybody has a copy of this virtual computer. And everybody run it. So, and basically when you do a smart contract transaction or deploy a smart contract, you are deploying it on that virtual machine. And so concretely, in order for this to work, we need that all the nodes be able to run this computer. So basically, the network can go only as fast as the smallest node in the network. And that's why the maximal scalability at peak level is 50 TPS on Ethereum, and I believe something around 20 TPS on average. Oh, okay, wrong. Okay, so the idea in order to increase this number of TPS is to resort to zero knowledge proof. So basically, instead of sending your transaction on Ethereum directly, you send it on Linea. The user experience is designed to be as equivalent as possible. And that's really the point of ZK is we want the smart contract system, so the virtual machine that we run, to be strictly the same. And so you can send it on the Linea network, and the Linea network is going to process all these transactions and prove their execution and send the proof on Ethereum. And the thing is, it's much faster to verify the proof than to verify other transactions. In fact, it's even much better than that. Whether you have one transaction or 1 billion transaction, the proof is going to take exactly the same amount of time to verify. That's a very, very powerful. So snarks are a very powerful tool for scalability, and that's why we need them for to have a scalable ZK. Okay, so now what I'm going to explain to you is how does that work for us. So our first thing to consider is there are many shades of ZK EVM, because if you try to emulate perfectly the Ethereum virtual machine, it's going to be super, super hard to generate a proof. And if you can, so you can make some compromise. So if you don't do any compromise, you're type 1. If you do a little bit of compromise, but overall the user experience is unchanged, you're type 2. And if you add more compromise onto that, you would be type 3. And if so that would be solidity compatible. And no, type 4 would be solidity compatible. And as you make more compromise, you can make some trade-off to have better performances. So Linea is type 2. So that's what we target. Okay, so how does all of that work? So the proof system is fairly complex because GVM is fairly complex. They involve a lot of cryptography and math. So I'm not going to dive in all the details, but I will give you, I hope, some highlights on and some outlines on how all of this is structured. So we have 4 components. The arithmetization. The arithmetization, basically, its goal is we take transaction in and we turn this into math. And the goal of Arcade and Vortex is to take this math problem and convert it into a proof. And the goal of it is to generate the proof as fast as possible, but without too many restrictions on how small it should be. And then we apply another proof on top of the past proof. Namely, we generate a proof that the Vortex proof was correct in what we call the outer proof, and we send the outer proof on Ethereum. So I'm going to, Vortex is what we call the inner proof system, so that the 2 squares, the 2 rectangles in the middle. So it relies on, I'm going to zoom more on it. It relies on lattice cryptography. It relies also on what we call error correcting code. So I'm going to dive a little bit more in this. It's allegedly post-quantum, plausibly post-quantum. I'm saying plausibly because a lot of claims are made about hash function or schemes to be resistant to quantum computer attack. But in reality, it only holds because we don't know such attacks. But maybe we'll discover it later. So that's why it's more common to say plausibly post-quantum. Okay. So let's look first in the arithmetization and try to understand a little bit what's going on there. So as I said, we get transactions and we turn that into math. So we are going to look at it, to look at the Ethereum virtual machine as a set of registers. For register, you can understand it as a small memory cell. which are going to evolve according to rules. And these rules are dictated, and the definition of this register are dictated by the Ethereum specification. So concretely, we take the Ethereum specification and we need to convert it into arithmetic equations. That is, arithmetic equation means just we can only use addition and multiplications. So let's take a small example. So instead of trying to arithmetize the EVM, we're going to just arithmetize a simple program. So say we have some number x, and we want to compute x to the power 256. So just to compute this value, there is an algorithm which is to repeatedly square x 256 times, and at the end you would get the result. And so for this kind of computation, we can generate a trace. And in order for it to be a correct trace, that does indeed verify that I computed x to the power 2 to the power 56. Then I need to enforce the following constraint. So first, the trace should start from x. The following, so every element should be the square of the past one, and it should end with the alleged results. If I can generate this trace, then you know that I did the computation correctly. You can use it to audit the computation. And the idea is that we're going to do exactly the same thing with the ZK-EVM, except that instead of having a single column in my traces, I'm going to have plenty of columns and much more complex equations. But really, that's the idea. So if we look at the Ethereum virtual machine from far away, so we can see that it contains several modules. It's based on a stack. There is a memory. You have a storage where you can either see the account, the storage of a contract, or you can access to accounts living on Ethereum. You can also access to the smart contract code. There is some gas measuring module, and there is a program counter like in many CPU architectures. And so we model all of this module per module by enforcing that each module works as a separate subcomputer and they communicate truthfully, meaning according to the Ethereum specification. So each of these modules can be seen as a table. So it's not one single column, it can be many columns. Can think of a table really in the same way as you could think as an Excel spreadsheet. And in order for the module to be correct, then you have Excel formulas that should be correct. That really is the way you should think of it. So for instance, here I can describe a constraint b minus 2d equals 0. So that's an arithmetic constraint because I'm only using addition, subtraction counts as addition, and multiplication. And basically it will enforce that b always contain d multiplied by 2. That's not very useful per se, but it's just to give you an example. And that's fairly consistent with another approach taken by a proof system named Plonk, if you know about Plonk. And we also have other more complex type of constraints. So we have what we call lookup constraints. Basically, we use them a lot when we want to enforce that that some module communicated truthfully, and by saying that some set of columns should be included in some other in the module. And we can use it to emulate that some module took some data from columns from another module. And so this way, by doing this, a lot of this constraint, we can emulate the EVM. So concretely speaking, the way to do it is not to do the arithmetic constraint manually. We in fact developed a high-level language which can encapsulate more complex logic, but at the end, it all boils down to arithmetic constraints. Okay, so here's a view of concretely what are all the modules. So it's a bit more complicated than the picture of the EVM you saw earlier. And this is in fact outdated from 6 months, I believe. and a new version of the specification is going to come, and it's going to be even more crazy. We've been working on this for 1.5 years now. Yeah, it took us that time to develop all of this. No, not in the right order. Okay, and so basically what I presented to you is a way to turn a description of a specification of the Ethereum virtual machine into a set of arithmetic equations. So that's into our mathematical constraints. And so when you run transaction, the ZK EVM is going to generate execution traces that are exactly a spreadsheet in the model we defined earlier. And if this corresponds to a truthful EVM execution, then the constraint holds, and we are happy. So now we need to prove that the traces exist and are correct, and we know them. Okay, so here it's going to be a little bit more difficult to follow. So don't worry if it's a bit hard. I will be also a bit fast because I'm already halfway through the presentation, and that's not necessarily the most interesting part. So the idea is that what we have to prove is that some traces satisfy some constraints, and we want to turn that into something more homogeneous because we have many types of constraints, not very easy to work with for the prover. So the goal is that we're going to turn that into polynomial evaluations. So in order to do that, we use what we call the interactive oracle model. And this gives us a framework to turn this protocols that can verify traces into protocols that generate proofs, only requiring polynomial evaluations. So the oracle is basically a trusted third party which never lies. Peggy is the holder of the traces, so that's me, I'm the prover. And Victor on the right is the verifier, so that's you want to be convinced that the traces are correct. And so basically the way we can do it is to let me send to Oscar, the trusted oracle, all the traces, and you can ask Oscar, the third party, whether those constraints are correct. So that's nice, but it requires a third party, and that's not what we are there for. So we need to somehow turn this protocol with a trusted third party with a protocol with cryptographic assumption instead. And so basically the idea is that at the beginning, Oscar can answer all the queries as you want, and at the end, you should only be able to evaluate polynomials based on that. And so basically I apply compilation step, which are small iterative transformation to the protocol to get to this point. And at the end, we want to remove Oscar by replacing it by a polynomial commitment. And that's where we go to Vortex. So I'm going to dive more onto this one. Sorry if I was very quick. Okay, so Vortex, how does that work? So basically, we had to sum it up. We had traces. We wanted to know whether they satisfied some constraint, and the Oracle compilation with Oscar allow us to turn this into a protocol where I'm not interested to just know if the traces satisfy the constraint. I just want to evaluate some polynomial corresponding to the traces. So that's much more homogeneous from mathematical point of view, even if it doesn't make a lot of sense right off the hat. And so once we are at this point, the idea is that instead of using a trusted third party, we're going to use a polynomial commitment. So a polynomial commitment allows you to send a commitment. It is some sort of fancy hashing of the traces, which are going to be served as part of the proof. And as a verifier, you're going to wonder whether the polynomials represented by this commitment satisfy some property or their evaluation satisfies some property. And you also want to check that I do the evaluation correctly. And so that's what the polynomial commitment is doing. So it relies on lattices, and it relies as well on error correcting code. So what is a lattice? So a lattice is a multi-dimensional. So here on the slide you have a lattice in dimension 2, but you could have really reuse much more dimension in practice, and you can view it as a set of points repeating periodically within the entire space infinitely. And so you can generate a lattice with two vectors, b0, b1. And the idea is that the lattice should be generated only, can be generated only and always by moving according to b0 or b1. And so why is it interesting in cryptography? And it's interesting in cryptography because we know hard problem involving lattices. One of them is fairly simple. I give you b0, b1, we generate a lattice, and you need to give me the shortest vector inside that lattice. So it's kind of easy in small dimension. So I let you check, but 2b0 minus b1 should give you the results. So that's kind of easy. But if you do it in dimension 100, it becomes absolutely impractical. In fact, it is so hard that even if I give you the correct solution, you can't just check it for yourself. So that's really a hard problem in mathematics. And we can rely on some version of this problem to do cryptography. And more specifically, we can do a hash function, which I'm going to describe now. So say that we have a list of numbers and that these numbers are all smaller than 8, just to simplify. So how does the hash function work? So first you split the number in bits or small limbs. So here we have the corresponding decomposition. So it gives you a vector, and you can compute a matrix vector product. It gives you the hash. Like, it's just as simple as this. It gives you a collision-resistant hash function, which is secure under non-cryptographic assumptions. So really a good one. We can't use it as a random oracle, so it's kind of limited for the use case, but for what we want to do, it does everything we need to. So since it's very simple, then it's also very fast. It's secure, plausibly secure against quantum computer. Very easy to accelerate through hardware or just SIMD parallelism. And its security, as I said, is linked to a studied lattice problem. So it gives us a lot of qualitative guarantees regarding this hash function, which is kind of comforting. But on top of being fairly easy and to implement and fast, it's also very easy to prove because we only need to check that the limbs are small and that the limb decomposition was done correctly. And we only need to check that a matrix vector product was done correctly. And that's really, really simple to do in with zero knowledge techniques. And on top of that, if you have a lot of those hashes to do, it's very simple to, like you can even optimize the proving. It really has a lot of nice properties. So if we plot a little bit traditional hash function, also so-called snark-friendly hash function, we see that there is always a trade outside of lattice-based hashes. There is some sort of trade-off. So you have to choose either your hash function is fast, either it is very efficient to run in a snark. And with lattices, you have sort of a good trade-off between the two. So that's why we are very excited with them, and we choose to work with them to develop the prover and the polynomial commitments. Okay, so now I'm going to go on with the error correcting code. So I said there was lattices, but there were also error correcting codes. So error correcting codes are a tool that is commonly used in telecommunication. So basically, when you send something with your computer, then you send some signal, and this signal always gets somewhat altered throughout the communication. But sometimes we still want the message to be perfectly delivered. And for that, we use error code. So the idea is we take the message and we encode it. And importantly, the encoded message has to be bigger than the original message. I will explain to you a little bit more later, but it's going to be clear. And the idea is that even if there are some errors in the error correcting encoded message, then I can still recover the original message and correct the error, and it's like nothing happens. So they are kind of very useful, used all over the places in telecommunication, also for persistent storage, hard drive, also in RAM memory. It's a very common tool, but it's also very useful in cryptography. So here's an idea of error correcting code. So say I just want to say hello world, and I will just repeat 3 times hello world. So if one of the repetition is altered, then you can still recover the original message. So it's not a very great error correcting code, but it's a simple one. And basically, if you have some errors, but not too much, and not at the wrong position, then you can vote for each letter, and you can recover the original message from that. But in practice, we don't use that. What we use is an error correcting code named Reed-Solomon. So now, instead of repeating your message, you encode it as a polynomial, and the encoded error correcting code is evaluations of this polynomial, many evaluation of it. And the thing is that even if some of these evaluations are altered in what you communicate, I can still recover the original polynomial through the BCH algorithm. Not going to explain the BCH algorithm, but I can show you a little bit the mathematical intuition behind it. So the thing is that your message is defined uniquely by the 3 numbers A, B, C. And so that gives you a parabola. And the evaluation points correspond to points in the plane. And the idea is that in order to recover the message, I should find the parabola that goes through the most point as possible. And if I can, then I have the best candidate for error correction. And if there are not too many errors, I can always find a unique parabola. And so in practice, it's much more, for what we do, it's much more interesting. Okay, so how does the polynomial commitments work? Exactly. So remember the traces? Okay, so here we have the traces, except that you have to tilt your head on the left to recognize that we just rotated the traces diagram by 90 degrees. So we lay out all the traces in a big rectangle, and each column in the traces now becomes a row. And we view them as a polynomial that the verifier wants to check evaluation of. So what we do is we encode each row using our Reed-Solomon code. We hash each, so we obtain a larger matrix with more columns. We hash each of the columns into using our sys hash, lattice hash. And this is our commitment. That means that if I just send you the black squares, then I am committed to the traces. So it's like when you send a hash of something to someone and later reveal what is the pre-image of that hash, then it's sort of work as a commitment. That once you're committed, you can't change your mind, and that's important for security. And so now that the verifier has a commitment to the traces, he now wants to be convinced about evaluation of these traces. So throughout the mumbo jumbo with Oscar, we have some claimed evaluations of the traces seen as polynomials. And now you want to be convinced that I did not lie when I claimed the evaluations. So in order to do it, you're going to send me a challenge, which is going to be a random linear coefficients of random coefficients for a linear combination. And I'm going to send you a linear combinations of the columns. And later, when you receive it, you're going to select a subset of the colon of the encoded traces, and I'm going to give them to you. And so now, with all of it, you should have the following data. And basically, if you want to be convinced that the evaluations were correct with respect to the committed data, then you should verify that the colon, when the selected colon are hashed, I obtain the same thing the second, the fourth, and the seventh squared. When you try to reevaluate the random linear combination, it should be consistent with the orange squared. And when you, the orange squared should be themselves a linear code. And when you decode it, the orange squared, because it's a correct code word, evaluate it at the evaluation point and try to compute the linear combination of the yellow squares, you should get the same value. And if you do all of this, then you're convinced that the traces are correct. And so we are right on time. So concretely, the proof size is square root of n. So say concretely, the traces contain like 5 billion cells, very big. And so the proof size and the verifier work is going to be only proportional to a square root of that. But that's much smaller than what we had earlier, but that's still quite big. So the idea is that we are going to generate later on another proof that the vortex proof was correct, and we are going to repeat. And that's going to be, each iteration is going to compress the proof. And at the end, we can make a prompt proof to get something very small. And that's what we call self-recursion. And time.
Okay. I have so many questions, but I'm going to, you stay on. I'm going to quickly bring Declan on to give some engineering updates. And then I'm going to hold you hostage for like 10 to 15 minutes as I ask you stuff.
Yeah, okay,
Is
sure.
that okay?
Yep.
Okay, cool. So, goodbye. See you soon. Declan, come up. I know you have some engineering updates for those of you who are building. I think it's probably especially our bridge partners, right? So take it away. I'm very keen to talk to Alexandre and not you right now.
So am I, to be fair. That was an amazing presentation. So awesome. Okay, I'll be quick. So hi everyone, Declan, product lead for Linea. Got some engineering updates to fill you in on the delivery side. So we're making some upgrades to our testnet very soon. And in a nutshell, there are kind of 3 key features I want to talk about. So the first is batch conflation. Okay, so what is batch conflation? So today on the testnet for each layer 2 block, which is every 12 seconds, we bundle those transactions into a batch, and then we send that batch to go early to the L1 to then be verified with a proof. Okay, as Alexandre was mentioning, right? But the issue is that what if you only have a few transactions in that block and in that batch, right? It's not very efficient because you have to pay for the fixed cost to verify a proof, and that kind of cost gets put onto users, so it's not great. What we've done with batch conflation is basically take each L2 block, take the traces from that block, and then concatenate them until we reach a theoretical limit, and then send the batch to the L1. Okay, so that means that we're sort of optimizing the number of transactions that we fit into a single batch before verifying the batch of a proof, which is amazing because that means we're going to reduce the cost for users, and it's also going to increase the user experience because we can think about reducing the sort of L2 latency to have faster blocks as well. So that's a really exciting update. The second one is we're going to be making an update to the smart contracts. Okay, so the smart contracts that live on layer 1 as well on L2. So the main rollup smart contract will be getting an update. We'll be updating the verifier. So as Alexandre was mentioning, there is an inner proof and an outer proof system. The outer proof system today is Graph 16. We'll be moving to Plonk with some custom gates. Good because it's a sort of trusted, universal trusted setup with Plonk, which is just far easier to upgrade. I won't get into the details. And then the other one is the message service, so the actual sort of canonical message bridge in the rollup. And what we're doing there is we're changing the model from what we have today into a sort of split delivery model where users can actually send a transaction which anchors the message on the L2 if you're going to bridge from L1 to L2, and then there's a claim step as well. And this basically delivers a much more robust and cost-efficient mechanism than what we have today. So again, getting things ready for the upcoming mainnet as well. And then lastly, on the smart contract upgrades, we're actually deploying a canonical token bridge. So there's the message bridge, which sort of sends messages between L1 and Linea, and then there's a token bridge which allows dApps and users to kind of move ERC20 tokens as well between Go Early and Linea. So we'll be deploying that as well, and that kind of helps to reduce liquidity fragmentation. And then the third thing is we're actually delivering API for our bridge partners. So this is called a Postman SDK. And basically, because of that update I mentioned where we anchor a message on the L2 and then claim it, we're actually going to have a SDK that dApps and partners can use, and we'll also run, it'll be permissionless, but we'll also run one where it actually handles that process for you. So from a user's perspective, the bridging will be very seamless. It'll be very easy, one transaction to deploy. So it's a bridge from Go Early to Linea or vice versa. So lots of exciting parts there. We'll also be making some updates on the security side. So thinking about the Security Council ahead of mainnet and how we'll actually manage upgrades moving forward. And over time, we'll keep removing those training wheels to make Linea a more trustless solution. So the three changes: batch conflation, update to the smart contracts, and adding a Postman SDK for the bridging. So yeah, all very exciting. And yeah, I hope to have everyone test it soon in the community.
Cool. Yes. So release version notes will be coming out soon, later today. We'll put up some documentation for the bridging and the SDK, I think within the next 2 days. If you have any questions, go ahead and just post them on our community support forum if you want to talk about exactly like how this might affect what you're building. But unless you have anything else, Declan, I don't want to talk to you anymore. I want to go talk about the prover.
I'm going to hang around as well. I might have some questions.
Okay, cool. So I will you have questions too? Should I just like leave you on screen so people can look at your face?
Yeah, I saw a question about oracles, so I can answer. So someone was asking whether oracle were some sort of AI. No, it's more, and the answer is no, not really. So concrete, to explain a little bit more, when we develop a protocol, and it's a common practice for every proving scheme, you first develop the protocol in an idealized model where you trust that the prover will not behave wrongly, but just for some specific actions that it does. And that's called a model. Is made to be completely unrealistic. It's close to a trust assumption, but the oracle is a way to formalize this, which is instead of asking the prover to be honest just for some operation, we just say that there is an oracle that is always truthful and honest.
Okay, cool. So can you share the screen of like the arithmetization / square block with like
Yeah,
vortex and arcane and then the one with like the orange arrows that point and say things are here?
Which one for vortex?
This one. Okay. So I'm going to summarize what I understood, and you can tell me what's wrong, and then we'll go from there. Okay, so to start off from like the very beginning, right? If you're not familiar with like roll-up architecture, there is a roll-up contract on the L1 that like stores the block, that's the data, etc. We don't really care about that right now. That's not the part that's important to you, right? There's a separate verifier contract on L1 as well that takes in the proof from kind of this like inner proof to outer proof to accept the data being like the let me start over. Okay. I'll go against this kind of image right here. So it starts off with transactions are being sent to Linea. In order for that information to get passed down to Ethereum L1, it needs to batch that up, like commit or push that through like a proof to say this is true or false. And then the verify contract on L1 will accept it if it's true. The thing that's special about here, right, is like how does that proof get generated? So it starts off with arithmetization. I don't know how that works, but basically what that's saying is how do you take a computer program and turn it to something that a zero knowledge proof can understand? That's the part where you're talking about changing into math, right? So specifically more so taking that computer program, changing into polynomials that the ZK proof can then interact with, right? So then once we get to the provers, okay, I'm gonna stop here. Let me know if anything's wrong. Otherwise,
No,
I'm
so
gonna
far
keep
so
going.
good.
So far, so good. Okay, cool. So now let's forget about like that block. Now we're in the second and third block. So that like dotted block and then the outer proof, right? So basically what that's doing is making the proof smaller and smaller and smaller to make it faster until we pass it in. The thing that is the outer proof, which I guess Declan mentioned, was like Groth going to Plonk, which I don't understand, but basically that's what kind of every ZK rollup is doing right now in terms of proving schemes, right? So that's not what makes Linea special necessarily. It's like the middle block that does. So we're gonna like say that's becoming Plonk. We're gonna ignore that right now in terms of explanation because we want to know what makes Linea different, right? So then we move to the middle part, right? So this is the vortex to arcane to vortex to arcane kind of thing. So I forget what arcane is, but let's go back to the weekend. Where should I start? So I think one thing I got confused on is like you kept saying polynomial commitment. I'm not sure what that is.
Okay. Yeah, maybe I should have made it clear. So a polynomial commitment is a cryptographic protocol technique. And so concretely, it allows you to first think about a polynomial, commit to it, which is an equivalent of fancy hashing your polynomial. So it's like a hash, but you can prove things about this hash, and we call that a commitment. And so you can commit to a polynomial, and then so you can send to me the commitment, and I can wonder what is the value of p, your polynomial, evaluated to 2, and you can prove that to me, and that's what's called a polynomial opening.
Okay.
And basically that's the idea. You can commit to a polynomial and you can prove evaluations about this polynomial, and I can verify your proof and be convinced that you truthfully evaluated the polynomial you committed to.
Okay, so is this specific to like I guess zero knowledge proofs? So like let's circling back to like zero knowledge proofs are cool because they allow you to reveal information without knowing it beforehand or like getting the full picture, right? And yes.
Yes, so it's true, but it's a bit confusing because the terminology we use everywhere in the blockchain world. So we say we generate ZK, zero knowledge proof. ZK is about privacy. It means I could mean something like I prove that I know the traces. So maybe the traces may involve some secrets like my balance, and maybe I don't want you to know about my balance, but that's not what we are doing here. What we are interested in is what we call the succinctness. I can come back to the one of the first slide. It's not about zero knowledge or privacy. It's about snark, in fact. Too many slides.
Okay, wait. So before you can keep looking for the slides, but I'm gonna re-say what I am. So basically, zero knowledge proofs are cool because of succinctness, and what that means specifically is we can remove a lot of information and make things smaller, so things are faster, and that's why
Yeah,
zero knowledge proof is
yes,
cool in this case, and we're not talking about like the hiding information part. It's more so reducing information is why
yeah,
we're
exactly.
using ZK proofs. Okay, cool. And part of the reduction process is going to be like those polynomial commitments, which basically is a way for us, like a cryptographic scheme, to say, I'm talking around it, but like revealing information without like giving the full picture, I guess, is kind of the polynomial commitment part.
Yeah.
I feel like I'm just confused.
Yeah. So basically, to sum it up, so after arithmetization, you had your computer program and you turned it into a set of traces. So that's what we meant when we said take a program, turn it into math. And turning it into math means specifying a set of columns, of modules and constraints. And when they are satisfied, it means that your program was correctly executed. And then you want to not talk about constraint, but you want to talk about polynomial evaluation. And that's the point with Arcane and Oscar.
Okay. Cool.
And then polynomial commitments.
Okay. I have more questions, but Declan, if you wanted to jump in before I like take over. No? Okay, cool. So going back to your explanation of the oracle. So to summarize, right, Oscar, the oracle, is there to convey information like between, I guess, Peggy and who was the other person? I don't remember.
Victor.
Victor.
Peggy like prover and Victor like verifier.
Okay, so Peggy is the prover, Victor. Oh, it makes sense. Okay, Victor is the verifier. So that's a verifier contract on the L1,
Yeah,
right?
exactly.
Okay, and then Oscar, the oracle, is there to convey information.
It's
Yeah.
there to be some sort of trusted third party. Basically, what we want is to convert constraints into protocol, and Oscar is a tool for that. And Oscar basically represents everything that has not been simplified yet. And the goal of Arcane is to apply a lot of, so we have many queries at the beginning. So when we specify the constraints, so it can be lookup queries, permutation queries, inner product, etc. And the goal is to have only allow Oscar to answer questions about univariate evaluation opening. Univariate means polynomial, but it's only a single value.
Okay, wait. So basically, I keep saying things. So Arcane contains what?
Okay, so concrete. Okay, maybe I can move on and it will be clear. So basically, when you specify the traces, you specify it using a lot of very complex constraints like lookups, permutation, global constraints, local. This constraint is what lets you know that the trace was correct.
Okay.
And the goal is to, and so basically you can start from, and Oscar is just a tool to represent what we have not reduced yet. So what we have to trust, or what is still yet to be proven or verified.
Okay. Cool.
So at the beginning, Oscar will answer every question that you have. And so basically it gives you the simple protocol where you just send, it's an abstract protocol where you just send the traces to Oscar, and Victor can just ask to Oscar whether the traces were correct, and Oscar will just say, yeah, that's legit traces, and you can and you know that it was correct. But the thing is, since Oscar is an ideal trusted third party, we don't really have a protocol in the real world. And the goal is to work out an actual protocol from this protocol by applying small transformation over this protocol.
Okay.
So it's a compilation, protocol compilation steps. I know it takes time to grasp it. So, yeah. But I wanted to explain a little bit how all of that works. But just to simplify, at the beginning, we have the verifier has questions about constraints that are complicated. And at the end, the verifier will accept by only asking to Oscar questions related to polynomial evaluation. So we no longer have complicated arithmetic constraints, we only have polynomial evaluation. And once we are at this point, we can completely replace Oscar and say that whenever you want to say something to Oscar, instead you will send a polynomial commitment of it. So you will send a polynomial commitment of the traces. And you will, throughout the protocol that we obtained by compilation step, ask to evaluate these polynomials at a random points. And so instead of asking Oscar to evaluate these polynomials, you're going to ask to me, Peggy is the prover, what are the evaluations of this polynomial? I'm going to generate these evaluations, and I'm also going to generate a proof that you can verify. And all of this put together make the proof. And the idea of why we are working with compilation steps and Oracle is because there is a very clear way to know whether what you're doing is secure or not, because you just need to analyze each compilation step by saying, okay, if the initial protocol was secure by allowing Oscar to respond to many constraints, then my transform protocol, where Oscar can answer to a little bit less constraints or questions, is still secure.
Okay.
So the goal is to simplify.
All right. So when we go back to that picture of like the rectangles with the things, can you map that to like the steps in here?
Yeah, correct. So all of it happens in Arcan. I don't know if you can see my cursor.
I can see your cursor, yeah.
Okay. So as I said, here we have transactions, execution. Poop, 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 it goes through arithmetization. And here we have traces. And basically, once we are at this point, the verifier is interested to know whether these traces are correct with respect to our constraints. And so there are many constraints. There are lookup constraints. There are permutation checks. There are global constraints. So everything I presented to you earlier. And we are going to map that to a protocol where we are going to introduce Oscar and let Oscar respond to this question for us. So now that we have Oscar, we want to progressively remove from the scope of Oscar some of the questions. So we are going to emulate a protocol. We are going to use protocol that use permutation checks to remove the lookup check, for instance. If I come here, like the first thing we remove is a lookup. And we say, okay, instead of doing this lookup, I'm going to create a new column, use a random challenge. I'm going to have a cryptographic protocol, which counts as a compilation step, which is going to prove the lookups, provided that some permutations and global constraints are correct. So I effectively, by doing this compilation, I effectively removed lookups from the scope of the oracle, and we have a less powerful oracle. And then I will remove the permutations and the globals and the local, and then I will make sure that we have only polynomial evaluations. And so once I have done this, instead of having questions about whether some traces satisfy some constraints, you will have some questions about whether some polynomials represented by the traces are evaluated at a given random point. And the polynomial commitment is there to address these questions that you may have. I don't know how clear that was.
Okay, I kind of get that part. And then so vortex is the lattice proof part.
Yeah, exactly.
Okay.
And the lattice proof is only there to check polynomial evaluations.
Okay. So if you go back to the previous slide with the Oscar or the weekend Oscar.
Okay. Yeah.
Not this one, like the square. I got a little confused because it makes it seem, is it the proof? Like I'm trying to like figure, like, does Oscar fit into the arcane box, or is that more so when the lattice
Yes,
proof?
exactly.
Okay, okay. So there was a picture with like a weakened Oscar in the square. It said simplified maths. I don't know if you know what I'm talking about. I got a little confused by like
Yeah,
uh,
exactly.
so Oscar is within arcane, and then it just like basically makes that information like it like let's just say like whatever it does stuff. The lattice based proof is going to be what's verifying it, and that is cool because it like I guess the trade off between like arithmetization and there's that one graph like faster run times it doesn't have, right? And so lattice based proofs
Yeah,
proving that is like really cool because we kind of get that like the
yeah,
best of both worlds. And then that's kind of maybe this is a question for you, Declan, or maybe you know this, Alexandra. Um, basically, when we think about roll-ups, right? One of the I guess vectors we think about is like prover time, right? And so each kind of roll-up has their own way of going about it. I think your slide that you briefly touched upon, lattice-based proofs, is like you said compatible or easily compatible. For example, if we were exploring like hardware acceleration,
yeah,
but at least on the Linea side right now, our research is really focused on speeding up the arithmetization and then this inner proof. And that's where we're kind of saying that the real speed is going to be coming from. Yes.
yeah,
No, maybe so.
yeah. Can you hear me?
Yeah.
Okay, okay.
You're saying yes?
Yeah,
Okay.
yeah, I was saying yes.
Okay. I think that's probably the most important part for somebody who doesn't understand anything but somewhat cares. um yeah. I skipped my next meeting for this conversation, so I should probably attend it. But Declan, do you have anything you wanted to add or ask or clarify?
Yeah, I think something that might be interesting is so often people talk about like bits of security for these types of systems. Kind of
Yes.
curious. Yeah, Alexander, maybe you can like just touch down into like, how we're thinking about security and kind of bits around that.
Okay. So concretely, there is an important security property for SNARK protocol, which is called soundness, or more importantly, also knowledge soundness. But I will just basically knowledge soundness means how hard is it for someone who would like to cheat to generate a valid proof without knowing any traces or only knowing fake traces. And what the security bits measure is the amount of time it would take for such a malicious adversary to generate a fake proof. And what we say with having 100 bits of security means that it would take 2 to the power 100 atomic operation for a malicious adversary to generate a fake proof. Which is the level of security that we use for the prover.
Awesome. Yeah, 2 to the 100. Would you consider like what is sort of the target you would say to have ultimate like different levels of security? What would you say is like the goal?
Excuse me, I did not understand.
So like in terms of like for the community, maybe like what would you say is like the range of like bits of security from like the lower level to maybe like the higher levels?
Yeah, I think 100 is definitely the minimum. So we have seen some system running at 80 bits of security, but really that's to give you an order of magnitude, that's roughly the number of hash ever generated on the Bitcoin network. So it's not easy to generate that much computation, but it's definitely on the possible at a human scale. When you do cryptography, you should be orders of magnitude over human scales. Like it should really take millions of years for the entire humanity to break a single proof. That's a minimal level. And the reason for that is that you want to have some margin with respect to what is actually possible. Because maybe we could say, okay, like it took 10 years for the entire humanity to make 2 to the power 80 hashes on Bitcoin. So maybe it's secure enough. I mean, if it takes that much power to hijack my bank account, then I should be safe. Yeah, but maybe in 10 years, cryptographic algorithm attacks, etc., will improve, or computing powers. And then it will not be 10 years for the entire humanity. It will be maybe 2 months on a single computer, and then you have a problem. So no, you should be much higher than this. So 100 bits of security is considered a fair trade-off between concrete security, and if, of course, you could take 1,000 bits of security, but then the protocol would be incredibly slow. So yeah, I would say a fork between 100 and 128.
Nice. So key takeaway for the audience is community is that we have great security on Linea with 2 to the 100. Nice, thank you.
Okay. Wow, that was a lot. I don't even know if anyone was actually here for all of it, but cool. This is helpful. I'm gonna try and do a write-up, and
Okay.
then you tell me afterwards. You bring your red marker and cross all of it out.
Okay, I would like to.
Yeah, and then I'll post it on Twitter, and people can critique and share and retweet as they wish. Okay, awesome. This is very exciting. I'm so glad you were able to come on. You as well, Declan. Thank you for adding that tidbit about security. But yeah, we are over time. So thanks for everyone who stuck around. I had a lot of fun.
Thanks for having us.
Hey, bye.